Hi guys, so today we're going to start limits, so make sure that you have your limits notes out. We're going to start with a review. We talked a little bit about limits when we discussed polynomials and end behavior. So a little reminder, end behavior is what happens on the ends of the graph. So for example, in number 1, the graph goes up on the left and down on the right, but we wrote this in something called limit notation. So limit is the value that a curve approaches as it heads to a certain value. And that value could be infinity or it could be a certain number. Okay, so looking at this notation here, the limit as x approaches c, that little arrow means approaches, of f of x will equal the limit. So when we wrote end behavior, we wrote the limit as x approaches negative infinity and the limit as x approaches positive infinity, meaning what's happening on the left side of the graph, what's happening on the right side of the graph. So a little review, the limit as x approaches negative infinity, it's going down, is equal to negative infinity. That says the left side is going down. And then we have the limit as x approaches positive infinity. That's also going down. So that's also going to equal negative infinity. Let's do another one. Number 5. This one goes up, up. So the limit as x approaches negative infinity of f of x equals positive infinity. And the limit as x approaches positive infinity of f of x is also positive infinity. Let's do one more. Number 7. So this time the left side goes up, the right side is getting closer and closer to -4 because there's a horizontal asymptote there. So the limit as x approaches negative infinity is still positive infinity because it's going up, but the limit as x approaches positive infinity is going to be equal to -4. All right, so if we continue this idea, what if c is a certain value? What if we're saying as it approaches 2 or 4 or something like that rather than infinity or negative infinity? So we're going to start by using Desmos to kind of visualize this. Now, you're not going to have Desmos on your test, but we need to know kind of the big idea of what's happening here, okay? So I've gone ahead and I've typed this into Desmos, and we're looking as x approaches 2, okay? So if I go back, this is my graph. Remember, to get the table on Desmos, you can hit the settings and then go to table. So I want to know as it's getting closer to 2 from the left side. So starting at 1.997, 1.998, 1.999, and you may be able to see already, hey, it's getting close to a certain value. It looks like it's approaching -0.75. So at this point, you could type in the exact value. Sometimes that value won't exist, though. There may be a hole there. So let's see from the other side what's happening. 2.001, 2.002, 2.003. And notice again, it's getting closer and closer to that -0.75. We'll talk about this later, but that 2 doesn't necessarily have to equal that, but it's approaching that value from both sides. In this case, it does equal -0.75. So hopefully you saw that table on the Desmos, so I'm not going to retype that, but that means the limit as x approaches 2, meaning coming from the left side, coming from the right side, it's getting closer and closer to that -0.75. All right, so we're going to do the same thing with these examples here. The limit as x approaches 4. So as it gets closer and closer to 4. So I'm going to get rid of that one, and we're going to turn on this graph. So the easiest way to visualize this is, hey, what's happening on the left and the right? What's happening a little bit smaller than 4? What's happening a little bit bigger than 4? You can see that they are approaching 10. Okay, next one, as x approaches -3. This one is a rational function. So if I go into my rational function, we're looking as x approaches -3. So notice on this one, if I type in -3, it's undefined. So that point actually does not exist, okay? But actually, let me go back a step. and turn that graph on. Okay. So -3 actually does not exist, but what if I went on either side of it? So -2.999, -3.0001, and notice that it's coming closer and closer to that -4.5. So even though the actual value does not exist, looking on my graph, it's going to get closer and closer to that -4.5. All right, and one more on the graph, and you should be able to look at a graph or a table and tell me what that table is, or what that value is, or what that limit is. Okay, let's do one more. So I'm going to turn on this graph. We're looking as x approaches 1. Again, if I type in 1 exactly, it's undefined, but I can go a little bit to the left and a little bit to the right to see what is it approaching as it goes towards that value. So a little bit less than 2, a little bit more than 2, so it's approaching 2. All right, so a limit fails to exist. We say a limit does not exist in one of these three cases. It contains a jump discontinuity, meaning the left side is approaching one value, but then it jumps up and the right side is approaching a different value. You see these a lot in piecewise functions. A vertical asymptote, which is the same idea, because on the left side it goes down, on the right side it goes up. Or it oscillates, which basically means it goes up and down many, many times at that value of C. So let's do a few examples. I'm going to come back to number 18 in a second. I'm going to first do number 20. Now, number 20, same thing. We're looking as x approaches 3. So I'm going to turn on that graph. At 3 exactly, it's undefined. If you were to factor this, it would be a fact x minus 3 would cancel out, meaning it would be a whole. But let's look a little bit smaller than 3 and a little bit bigger than 3. Notice it's getting closer and closer to -1.16 repeating, okay? That's also equivalent to -7.6. Okay, let's look at the next one. Limit as x approaches 1. All right, so looking at my table here, I see that 1 is undefined. That would be a hole in your graph. But let's go a little bit smaller and a little bit bigger. And see, as it comes from either side, it's going to get closer and closer to that value of 0.1. Okay. All right, next one. We are looking here as x approaches 3. So if I type in 3, I see that it's undefined, meaning that it's either a whole or a vertical asymptote, okay? So if I go a little bit smaller than 3 and a little bit bigger than 3, I notice that both sides are approaching the same value. Both sides are getting closer and closer to -6. So either way you come from either side, it's getting closer and closer to that -6 value. All right, so now let's look at cosine of 1 over x. This one will look a little bit different. Okay, we're looking as x approaches 0. Now, notice without even looking at the table, okay, I can see that that goes up and down a lot at that value of 0, meaning it oscillates. Let's see what that looks like on the table. So here it's at -0.9. And here it's at -0.9. So even though it's going to approach the same value here, that doesn't mean, because if we look at our graph, it's going to be up and then it's going to be down. It's going to be up and then it's going to be down. So if I were to see that, you need to be able to recognize that on the graph, okay? To see, hey, that's oscillating, so that limit does not exist. Okay? All right, negative cosine squared of x. Let's look at that one. Okay, I'm going to turn on that graph. Now this one, we're looking as x approaches pi over 3. Okay, so if I type in pi over 3, this value actually does exist on the graph. So you can define it at that -0.25, but let's look at it as well as a little bit bigger and a little bit smaller. Notice in both those cases, it's getting closer and closer to that -0.25. then tangent of x. So for tangent of x, all right, going back here. All right, tangent of x, we're looking as x approaches pi over 2, which is undefined. If I do a little bit bigger, or a little bit smaller, oops, let's get out of that fraction. Notice that this one is negative, but this one is positive. So what that's saying is at pi over 2, if I were to make a new line down here, x equals pi over 2, notice that that is a vertical asymptote on the graph. So when I'm a little bit bigger, okay, that means I'm coming from the right side. So it's going down. The right side is going down towards negative infinity. On the left side, when I go a little bit smaller than the value, it's headed up towards positive infinity. So up on the left, down on the right, we don't know what to call that, okay? So therefore, they're going different places on the left and the right. We say that that does not exist. All right, so going back to our piecewise, if the limit exists, like I just said, it needs to be the same on the left and the right side. So otherwise, we're going to jump in your graph like a piecewise function. This is a piecewise function, okay? So let's look at what it's going to be on the left side. So negative 1 squared plus 1 gives me 2, okay? So on the left side, it's going to be headed towards 2. On the right side, negative 1 minus 2, it's going to be headed towards negative 3. So one of them will be stopping, the left side will be stopping at 2, but the right side won't be starting until it'll be starting down at negative 3. So therefore, that's different on the left and the right side, so we say the limit does not exist. If they were the same value, let's say 2 and 2, the limit would exist and the limit would be equal to 2. All right, so in some cases, the left and right side are both increasing without bound, meaning forever, or both decreasing without bound. So for example, in this case here, even though this is a vertical asymptote here, it's not like one is going up and one is going down. Those are both headed up. So though the limit technically does not exist, we can say that this heads towards infinity because they both go up. Let's look at one of these examples. Let's look at number 33, 1 over 3x squared. All right, I'm going to turn that off and that one. So again, same sort of situation. They're both heading up. So I can describe, technically this limit does not exist, but since they're both going up, I can say that it heads towards infinity. All right, we're going to talk about one more thing today, which we've touched on a little bit already, and that's one-sided limits. So I want you to flip to the page that says one-sided limit. So sometimes, even when the limit does not exist, I can still describe what's happening on the left side and what's happening on the right side, okay? So for example, looking at this graph right here, this notation right here says as x approaches 2 from the left, this little negative, as it's not an exponent, but it looks like an exponent, means what's happening from the left side. So if I look at 2, which is right here, the limit does not exist because it's going one way from the left side, one way from the right side. Doesn't exist. But when I'm coming from the left side, only looking at from the left side, I can describe what's happening. It's approaching negative 1. Same thing here, when there's a plus as the exponent, that's saying I'm coming